To start our unit on redox, we're going to take a look at oxidation and reduction. And redox basically is the short version for reduction, oxidation. So what are we talking about when we talk about reduction and oxidation? So today, one of the first things that we're going to do is actually define these terms. And then today as well, I'm going to show you how to determine the oxidation number of substances. Now, when we say oxidation and reduction, we're talking about the gain and the loss of electrons. So we're talking about the transfer of electrons. And we'll talk about what we mean by reduction and what we mean by oxidation. And unfortunately, some of these terms that we use are based on historical and industry reasons, and so they're not necessarily the easiest to understand and remember. But I don't know any student who doesn't work on this for a day or two and has it figured out. So today may be a little bit confusing, but stick with it and you will get this by the end of in a couple of days. So for a redox reaction to occur, you must have both reduction and oxidation. And if you don't have reduction and oxidation, it's not a redox reaction. Now, this is not a new category of reactions. Other types that we've looked at are also redox reactions. So for example, formation reactions are redox reactions. So one element has gained electrons, another has lost it. Decomposition reactions are also redox reactions. Single replacement is a redox reaction, and combustion as well. And then the special cases of combustion we've looked at, photosynthesis and cellular respiration. Now, have you seen that there's one group of reactions that's missing? And that's double replacement. So double replacement reactions are reactions. They're just not a redox reaction where the transfer of electrons is involved. So one of the questions that they always like to ask on the diploma, and I like to ask as well on unit tests, is which of the following reaction is not a redox reaction? And usually I'm going to show you guys how to find oxidation numbers to determine that. But a much faster way of doing it is figure out which of the reactions is a double replacement reaction. If it's a double replacement reaction, it's not a redox reaction. But again, like I said, we'll get into more of that as we learn about what redox is and reduction and oxidation are. All right, so we're going to get going on this. And basically, these terms came from the processing of metals, so metal ores, and also from rusting. So you're going to see that, when we describe what these words are, that's where it comes from. So historically, reduction was the formation of a metal from its ore. So when you mine for a metal, you start off with an incredibly large volume of ore that has the metal in it. And basically what happens to it through its processing, it's reduced to a much smaller volume. And that's where the word reduction came from. So for our purposes though, now what we actually mean is a gain of electrons. So that's what we mean by reduction. Now, I've got an equation here that shows this. So this would be nickel ore, NiO would be nickel ore, plus hydrogen, resulting in nickel, the pure form of the metal, plus water vapor, or liquid water in this case. Now, I'm just going to focus on the nickel because the nickel is the one that's undergoing reduction. In this equation, nickel has a 2+ charge, right? Because it's nickel 2 oxide. And here, nickel is just a nickel metal, so it's got no charge whatsoever. So do you see that nickel 2+ has gained electrons to become nickel? And we actually write that using something called a half reaction. So a half reaction focuses only on one element of a redox reaction and what's happening to it in terms of electrons. So here, again, I'm going to focus on my nickel ion. Okay, and it's 2 plus, not plus. And it's becoming nickel. Okay, solid nickel without a charge. Okay, so it's gained some electrons. Now, I have to add electrons to here. And one thing you need to know with half reactions is just like a regular chemical equation, it must be balanced. So the same number of atoms must appear on both sides. And the other thing that must happen is that the charge must also be the same on both sides. And to balance the charge, remember that in a chemical reaction, the only thing that moves are the electrons. The protons don't move. So I'm going to have to add electrons either on one side or the other side of the arrow. And here's the trick with this. The electrons always go on the more positive side. So do you see here that on the left side of the arrow, my overall charge is 2 plus? On the right side of the arrow, my overall charge is 0. So I'm going to add electrons to bring my overall charge that's the same. I want to bring it to the same as the least negative, like the least positive side. My apologies there. So I hope that you guys can see that I need to add 2 electrons. So now I have 2 positive, 2 charges, 2 negative charges. Overall net charge is 0. And on the products there, I've got a net charge of 0 as well. So one of the things that we say is that these substances that undergo reduction become more negative. And you can see that that happened here, right? Nickel went from 2 plus to 0, so it became more negative. I'm going to talk about the last 2 bullets in a moment here. And we're going to go back. Now we're going to look at oxidation. And again, the idea behind it, historically, it was to react with oxygen. But you will see with our examples that a lot of other substances can actually cause something to oxidize. So here is the example. So here's iron reacting with oxygen to form rust, Fe2O3, or a kind of a precursor of rust. Here, again, I'm interested in the iron. I'm not interested in the oxygen. And you can see that my iron went from no charge. And if you take a look at the charge here, it's actually 3 plus. So you can see that we had a loss of electrons. So again, what I need to do is I need to do my half reaction where I focus only on the element that I want. And what I'm going to do is basically write down the element that I formed there, or the ion that I formed. And now I need to decide which side do the electrons go on. So remember the trick, they always go on the more positive side. So do you see that this time it's the Fe3 plus that's more positive? I need to bring it to, in this case, 0. Remember, it doesn't have to be 0, it makes it equal. It's got to be equal on both sides. So I'm adding 3 electrons. All right, so 3 plus 3 negative, my overall charge is 0. The overall charge on the iron on the left side is 0, so my charge is balanced. So this becomes more positive. All right, so for our purposes in chemistry, an atom undergoes reduction if it gains electrons and becomes more negative. An atom undergoes oxidation if it loses electrons and becomes more positive. So here comes where it becomes a little bit confusing. And there is something else that we use to describe these substances. We call them oxidizing agents and reducing agents, and it's confusing. So we're going to look at this little diagram that I've got here at the bottom. And we're going to start with substance A. So you can see that A has these 2 electrons that it's going to give away. It's going to give them away to substance B. So you can see here that's what happened. So A lost electrons. It's undergone oxidation. But do you see that it caused substance B to be reduced? So atom A underwent oxidation, and in the process, it reduced substance B. So we call substance A a reducing agent. I know, it's confusing. So if an atom is undergoing oxidation, it's a reducing agent. The same thing happens with reduction. So here I have substance B. It's gaining those electrons from substance A. So it is taking them away from substance A, and substance A becomes oxidized. So substance B is undergoing reduction, but it undergoes reduction by causing substance A to become oxidized. And so substance B is an oxidizing agent. So think about an agent is someone, for example, that acts on the behalf of someone else, that helps somebody out, like if it's an agent for an actor, okay, helps that agent land jobs. Think about it this way as well. So substance B, by undergoing reduction, it's helping substance A become oxidized, so it's an oxidizing agent. Substance A, it's undergoing oxidation, but in the process of being oxidized, it's helping another substance become reduced. So it is a reducing agent. And again, I know it's confusing, but by the second or third day you're looking at this, you will get it. All right, so let's now finish off our table. It says a species undergoing reduction will be responsible for the oxidation of another species, and so it is called the oxidizing agent. And here, for oxidation, a species undergoing oxidation will be responsible for the reduction of another species and is also called the reducing agent. Now, our last blank deals with the next step in our lesson, which is learning about oxidation numbers. And substances that are reduced undergo a decrease in oxidation number. And like I said, we'll talk about that next. And a substance that is being oxidized will undergo an increase in oxidation number. So what are these oxidation numbers? So we're going to get going with this. Oh, and before we move on, just little things to help you remember. So there are two ways of remembering this. Oil rig. So oxidation is losing. Reduction is gaining. Okay, that helps you remember it. Or losing electrons oxidation, gaining electrons reduction. And it's Leo, basically we say Leo the lion. Oops, the lion says grr. Okay? So one of the things that I highly recommend that you do with this is when you are doing a worksheet, when you are writing a test, write that down on a piece of paper. Leo, either oil rig or Leo grr, and that basically you will always have that to keep in mind when I'm asking you if something becomes oxidized or reduced, or whether you have to figure that out. It's always something good to have on a sheet of paper. I do that all the time to help me remember. All right, now we can look at oxidation numbers. And these are hard to explain. Figuring out oxidation numbers isn't all that hard, but explaining what they mean is a little bit more difficult. So if this doesn't make 100% sense now, I'm hoping that as we get on and move on in the unit, it'll make a little bit more sense. All right, so it says, how do we know that a redox reaction has taken place? So there has been in the change in the oxidation state of two of the substances in the reaction, and I'll show you guys examples of that later on. So the oxidation state is the apparent net electric charge an atom would have if the electron pairs belong to the most electronegative atom. So the example I like to give with this is water. So water is a covalent or molecular compound. It's not ionic. And here's water here. If I look at the electronegativity, So the electronegativity of oxygen is 3.4. Of hydrogen, it is 2.2. So what we say is that its oxidation state would be for oxygen would be what its charge would be if it wasn't sharing electrons, if it had taken them. And in this case, you can see that oxygen would normally have 6 valence electrons. If it took the 2 electrons from each of the hydrogens, it would have 2 extra electrons. So its oxidation state would be 2 negative for oxygen. For hydrogen, again, because it's the least electronegative atom, it lost that electron. It had one to begin with. It now doesn't. So now it's missing a negative charge. So the oxidation state for hydrogen is 1 plus. All right. And this is not a real thing. So this is basically saying which atom has the greater affinity for the electrons. With water, they share electrons. So an oxidation state is just kind of a hypothetical charge that would occur if they weren't sharing the electrons. And so oxidation number is just a representation of the oxidation state. So in fact, oxidation state and oxidation number mean the same thing, right? So continuing on with that, oxidation numbers are not ion charges. Okay, so they're not ion charges. They are, okay, and do not represent an ion charge. However, atoms with charges, that's their oxidation state. But an oxidation number is not an ion charge. I'm hoping this will make sense as we do some examples. And again, the last thing here, the charges are written with the sign first as opposed to after to show that they are artificial and do not represent real charges. All right, so let's get going through these oxidation numbers. And again, I know you're probably a little bit confused with all that before. Let's do oxidation numbers first, and then we can come back and revisit that at a later date. So it says a pure element has an oxidation number of 0. So our examples here, I've got sodium by itself, I've got bromine diatomic, I've got phosphorus polyatomic. They all have an oxidation number of 0. So we have a tendency to write oxidation numbers on top of the atoms. I'm going to try, and it means going back and forth, but I'll try my best. So I like to use a different color. So all these atoms would have an oxidation number of 0. They have no net charge. They're an element by itself, an atom by itself. They have a net charge of 0. All right, our next rule. Our next rule says the oxidation number of a monoatomic, important thing here, monoatomic ion equals the charge on the ion. So I've got aluminum 3 plus. Okay, so its oxidation number is going to be +3. Selenide, the selenide ion is, and I'm going to write it here, Se2 minus. So its oxidation number is going to be -2. And do you see that we write the charge in front, again, to show the difference between a charge and an oxidation number. Now, the last example I'm going to show you is when you get an ionic substance that looks like this. So I have CaF, CaF2. So it's written as an ionic compound. You've got to split it up. So this is made up of Ca2 plus and 2 F minuses. So the oxidation number for the Ca2 plus is going to be +2. The oxidation number for the fluoride ion is going to be -1. All right. So again, for an ion, its oxidation number, it's going to be the ion charge. So Next one. The next one is hydrogen. So the oxidation number for hydrogen in compounds is +1, except for metal hydride. So 99% of the time, the oxidation number in hydrogen is going to be +1. But there are rare exceptions. So let's take a look at some examples and go from here. So our first one is H2S, a molecular compound. And here, the hydrogen, okay, its oxidation number, +1. Now, doesn't matter what the sulfur is doing. In fact, we use the hydrogen to figure out the oxidation number of the sulfur. We'll talk about that later. But whenever you see a hydrogen, its oxidation number is going to be +1, like I said. And you're going to see that, again, except for that one situation, which I'll give you one example of, but you'll rarely see. Here it is as CH4. Again, the oxidation number of that hydrogen is +1. Remember, this is a molecular compound. There is no charges here, but when you see a hydrogen, it's going to be +1. So when isn't it +1? And it is when it is acting as a negative ion. So the example here, NaH, okay? Do you see that sodium is going to be my positive ion and hydride is going to be my negative ion? So it's acting as a nonmetal. And it means that it's got to be together with a metal. It's got to be ionic. And only in this situation will the oxidation number be -1. And again, like I said, you will rarely experience that. Most of the time, the oxidation number on hydrogen will be +1. So, our next one, oxidation number on oxygen. And again, this is a case where 99% of the time you will see an oxidation number of -2, but there is an exception to that, so we'll briefly talk about it. Okay. So it says the oxidation number of oxygen in compounds is usually -2. So my first example is LiO2. And again, I'm ignoring the lithium. I can go back and figure out the oxidation numbers, and in fact I will at the end of this when I show you how to do that, but for the time being we're going through the rules one at a time. So I see oxygen, automatically oxidation number -2. My next example is KNO3. Again, I see the oxidation number is -2. And by the way, that's the oxidation number for one oxygen. So here you've got two oxygens, each with a -2 oxidation number. And my last example is the exception. So this is hydrogen peroxide. And you can see here, we were reading, it says, the exceptions are peroxides, which have an oxidation number of -1. So hydrogen peroxide basically has an oxidation number of -1. So the question that I get all the time is, wait a minute, so how do I know that a substance is a peroxide? And this is the best I can do with this to help you out. It is a substance that is going to be ionic. It's going to look like an ionic compound, and I'll give you guys a couple of examples. But it looks wrong. And you guys have done enough naming to know where it looks wrong. So CaO2 is a peroxide. This is calcium peroxide. Do you see that oxide would normally have a 2 negative charge? This should be CaO, but I've got CaO2. That means that that oxygen, right, is a peroxide. It's a -1. Okay, so again, you will see it often that it's going to be a metal. Oops, that's wrong. That's the same one. So if I have this, K2O2, most of you would say, wait a minute, that's wrong. It should be K2O, right? K2O2 is a peroxide. Okay, so this would be, again, oxidation number of -1. So again, they're going to be ionic substances. You see them with oxygen and you see, something is wrong with this formula. Okay, and then you look to see if it's a peroxide. Again, 99% of the time, you're not going to encounter that. Most of the substances you're going to encounter, the oxygen is going to be -2 for its oxidation number. All right, so here's where it gets a little bit more interesting. And it says, in molecular compounds, again, molecular compounds that do not contain hydrogen or oxygen, because we use hydrogen and oxygen to kind of guide us as to the oxidation number, the more electronegative element is assigned an oxidation number equal to the negative charge it usually has in ionic compounds. Oi. Okay, so let's go through examples. Okay, so my first one is going to be PCl3. So I have a covalent compound, no oxygen or hydrogen to guide me. So I now need to look at electronegativity. And I look at these two, and Cl is it's the more electronegative. Okay, it is 3.2. P is 2.2, so it's more electronegative. What charge does chlorine usually have? It has a -1 charge, so I assume that it has an oxidation number of -1. Now, there are situations here where this won't help you, and my second example is CS2. And this one has a problem. If you look at the electronegativity, you see that both are 2.6 in terms of electronegativity. So what you do then, I know this is so hard, you choose the element that's closer to the edge of the periodic table. So sulfur is closer to the edge of the periodic table, so we choose sulfur, and we give it the charge of its ion, which would be -2. And so for this one, it would be -2. And again, you're rarely going to come up with that situation where they're both the same electronegativity. You're more likely going to come up with the situation with PCl3, and you just choose the more electronegative one. I just wanted to mention that in case that ever popped up. I don't think I've ever seen it pop up on a diploma, but I just wanted to make sure that I talked about it. 6 is very closely related to 2, but I like to list it separately because sometimes it's good just to have this one in mind. And it says in compounds, the elements of group 1 and group 2 have oxidation numbers of +1 and +2 respectively. So I've got calcium fluoride. It's an ionic substance. I should be able to go just on ionic charge, but calcium is in group 2, so its oxidation number is +2. And my second one is NaI. It's going to be my second example. Again, another ionic compound, but sodium is in group 1, so its oxidation number is +1. All right, our last rule. And our last rule is, in a lot of ways, the most important one, because it will allow us to find oxidation numbers to all the different elements that I have not found an oxidation number for in these compounds. And it basically goes like this. It says, the sum of the oxidation numbers of the atoms in a particle must equal the charge on that particle. So I'm going to do this very slowly with one example, and then we will do it a little bit faster with another one. So my first one is going to be NO2. And for this one, it's basically the nitrite ion, so NO2 minus. And what this is saying is that the sum of the oxidation number of the atoms must equal the charge on the particle. So here I've got oxygen. Remember, oxygen has an oxidation number of -2 unless it's an oxide, and it's not an oxide here. Do you see that I have 2 oxides? So that means -2 times 2, I've got -4. And I like to do the math underneath, write the oxidation numbers on top, do the math underneath. Now, I don't know the oxidation number on this nitrogen. That's what I'm trying to figure out. But I do know that it's got to equal the charge. And do you see that the charge is -1? So basically, the number there has to equal -1. So whatever the number is, -4 must equal -1. And I hope that you guys could see that that's going to be +3. So +3 plus -4 equals -1. So the oxidation number of the nitrogen is +3. Now, the reason we do this is that oxygen's oxidation number is almost always -2. It doesn't change, but nitrogen can have a lot of oxidation numbers. So you use the oxidation numbers of the atoms you know to find the oxidation numbers of the atoms that change, and you can figure out what exactly it is in that situation. So our second example is going to be one that has, it's an ionic compound that has a lot of, I'm going to write it a little bit lower. So CaClO2, 2. Okay. So what I'm going to do here right away is I'm going to assign oxidation numbers that I know. And you guys see oxygen? There it is, -2. Now, the other one that I know, and this is the one that students forget, is I also know calcium's oxidation number. This is basically a calcium ion. So this, the charge on this, on the calcium, the oxidation number is going to be +2. It's going to match its charge. So now I'm going to do the math underneath. I've got +2. I don't know what the chlorine is. And my oxygens, and here you've got to be really careful. Do you see that I've got 4 oxygens? 2 times 2, okay, is 4. 4 times -2 is -8. And this has to equal the overall charge. Do you see that the overall charge is 0? There isn't a charge associated with it. So now I can figure out what that unknown is. And I hope that you guys figured out that that unknown is +6. Now, that's the overall total oxidation number, but I have to write the oxidation number per atom. And do you see here that I've got 2 chlorine atoms? So I have to divide this number by 2. So 6 divided by 2 is 3. So this chlorine has an oxidation number of +3. Now, the second way of doing this is by actually splitting it up into its ions. So I've got Ca2+, and I have Cl O2-. So again, using my oxidation number, +2, so I know that one, -2. This, and remember this is separate, okay, because I've separated them out. So -2 times 2 is -4. Remember, that has to equal -1. It's got to equal the charge. So what charge does each chlorine have? So it's going to have to be +3, because +3 minus 4 equals -1. All right? So what I'm going to do then is I'm going to go back and I figure out oxidation numbers for all of the other atoms. I'm going to color them in purple for the ones that I've done after the notes. And we're going to go back and we can now figure out all the other atoms' oxidation numbers that we ignored. And remember, these, why we don't assign them an oxidation number to begin with is because it varies depending on what they're bonded to. Oxygen and hydrogen and ions don't, okay? They don't change, and elements. Okay. So for here, H2S, I've got 2 hydrogens, each with a 1+ charge. So I've got +2, and then plus unknown equals 0, because it's overall neutral. So this becomes an oxidation number of -2. For this one, I have +4. That has to equal 0. So that has to be -4. So my oxidation number on the carbon is -4. And this one, well, this one I could have figured it out. It's an ion, right? So it's going to have a +1 charge. Okay? This one, LiO2, again, it's an ion. I can do that or I can figure it out either way. Okay. Oh, I see what I did. I did a mistake there, guys. This should be Li2O. My apologies for that. Okay, for this one, K is 1 plus because it's an ion, so plus 1. So this gives me -6 for the oxygen, +1 for the potassium. So that has to be +5 to make that equal to 0. This is going to be, where am I? H2O2, this is going to be +1. This -1 times 3 is -3, so that has to be +3. -2 times 2 is -4, so this is +4. Okay. These are ions, so 1 minus. And -1 there. All right, so next part is a little bit of practice. And so what I'm going to give you to do, so please pause the video and see if you can do these questions, and then restart the video and we'll go over the answers together. Okay, so I'm going to go over these answers here, and it says to calculate the oxidation number for sulfur in sodium sulfate. So sodium sulfate is Na2SO4. So I can, again, solve it like one whole thing altogether, but for these polyatomic ions, I do like to solve them separately. I just find that it goes a little bit easier. There's no brackets to worry about. This one doesn't have it, but usually if there's brackets, they become a little bit more confusing. So again, I look at oxygen and the sulfur. I know oxygen, its oxidation number rarely changes. It is -2. -2 times 4 is -8. And then one number, what number? -8 equals -2. And this has to be +6. Okay, so the oxidation number on the sulfur is +6. For this one, you're going to see that we're going to find the oxidation number of everything, but I want you to take a look at the nitrogen after you're done. You're going to see that the oxidation number is different in every time for the nitrogen atom, and that is why we use oxygen and hydrogen and ions to help us out, because those don't change, or they do in oxygen and hydrogen but rarely, and so we can figure out the oxidation numbers of all the other atoms. So here we go. -2 for oxygen. I've got -2 that's got to equal 0, so that's +2. But I've got 2 nitrogen, so I've got to divide that +2 by 2. So this gives me a number of +1. So the oxidation number of the nitrogen is +1. N2 is 0, my favorite one. I love elements by themselves. I don't have to figure anything out. Nitrogen monoxide, -2. So that nitrogen has to be +2. NaNO3. My sodium is +1 because it's a sodium ion. My oxygen is -2. So this gives me -6 plus 1. So what number there? And I'm hoping that you guys can see that it's +5 for the nitrogen, because that has to equal 0. For NO2, -2. -2 times 2 is -4. It's got to equal 0. So that one nitrogen has to be +4. And the last one is ammonium. So this is hydrogen. This is +1. I have +4, and this has to equal +1. So that means that nitrogen has to be -3. -3 plus 4 is +1. All right. So last thing before we get you to do a little bit of work is calculating the oxidation, basically to figure out that sometimes the oxidation numbers can be fractions, and it's not as bad as it looks, actually. So it says sometimes oxidation numbers are not integers, but a fraction. Oxidation states involve whole numbers, so a fraction means that it is an average of the atoms in that particular compound. So basically what's going to happen if we have a fraction is all of the atoms of whatever they are, they're not sharing the electrons equally. Okay, so oxygen, -2 for a total of -2. This has to equal 0. I've got hydrogen, each hydrogen, oxidation number of +1. So this is +6. And so this one here has to be -4. So -4 plus 6 minus 2 equals 0. But I've got 3 carbons. So it's basically, I have to do -4 divided by 3. So I can have a fraction. And here, what it's saying is that the carbons aren't all behaving the same way. So some of them are gaining more electrons than the others are. And so overall, because I'm looking at the overall, that's the average of an oxidation number of -4/3. All right, so that's the end of this lesson using oxidation numbers. We're going to get going right away into using oxidation numbers to help us out in figuring out equations, which substance is being oxidized and which substance is being